Well, good morning. We're working on the applications, and I thought I'd put a couple applications on non-ferrous metals, and then we'll also get started on glass melting. So we'll start it today, and then next Wednesday we'll finish up the topic of glass. So for non-ferrous metals, I put in an aluminum reduction cell and an aluminum melting furnace, and then a copper smelting furnace and a copper converter. And then for glass, obviously it's a glass melting tank. So the reduction cell produces aluminum metal from alumina or aluminum oxide. The charge for this furnace, we discussed bauxite, is the hydrated alumina. So bauxite, and the flux is cryolite. It's Na3Al F6. So this is a very powerful flux that really lowers the melting temperature of alumina. So this is a rectangular furnace. It's actually an electrolysis cell. And the alumina from the bauxite dissolves in the cryolite flux, and it actually forms a solution of these ions. So Al plus 3, Na plus 1, O minus 2, and F minus 1. And the cryolite really lowers the melting temperature from over 2000 degrees C to about 800 degrees C. So we have a graphite cathode and a carbon anode. So at the graphite cathode, these complex ions, which contain Al plus 3, are reduced to liquid aluminum. So the Al plus 3 is reduced to aluminum metal. And then at the carbon anode, the O minus 2 that's liberated from the Al2O3, that reacts with the carbon anode and basically forms CO2, can also form some CO. So you can see when oxygen reacts with carbon, it's going to consume the carbon anode. So that has to be replaced periodically. So when enough aluminum metal accumulates in the bottom of this furnace, it's tapped, and then more bauxite is added, Al2O3 is added. So what happens for the reactions in this reduction cell? The graphite cathode is an electron donor. So the Al plus 3 ion plus 3 electrons forms aluminum metal in the liquid form. And then at the carbon anode, that's the electron source. The O minus 2 provides the electrons that react with Al plus 3 to form Al liquid. So O minus 2 becomes O2 gas, and the electrons that are liberated are reacting with Al plus 3 to form the liquid aluminum. So the overall reaction is just Al2O3 plus the carbon forming liquid aluminum, and then CO2 gas. So this is what the reduction cell looks like. It has a carbon lining, and then there's the cathode is in the bottom here, the carbon cathode. The carbon anodes are in the top here. This is where the alumina is charged into the furnace. So the red color here is the aluminum metal. The pink color is the cryolite bath that's floating on the aluminum metal. And then you can see the CO2 gas coming off. So these carbon anodes are consumable, and the CO2 gas comes off. So again, the overall reaction is Al2O3 plus carbon forming liquid aluminum and CO2 gas. This is a schematic side view of the same furnace. The backup lining, the insulation is usually in brick or castable form, and it's an alumina silicon material. Could be an insulating fire brick or an insulating castable. The inner lining is composed of the graphite cathode, and the sidewalls can be carbon. They can also be silicon nitride bonded silicon carbide. And the main issue here is corrosion from the cryolite bath. So the cryolite bath is sitting on top of the molten aluminum. So again, the carbon anode, 3O-2 yields 3/2 O2 gas, and then the 6 electrons. And then at the cathode, 2Al plus 3 plus the 6 electrons form 2Al liquid metal. So that's what the reduction cell looks like. There's another furnace for just remelting aluminum metal, and aluminum melts at 660 degrees C. So the charge here is simply aluminum ingots or aluminum scrap. And this is a round type furnace. It's a reverberatory furnace. So a reverberatory furnace just means it's isolating the material that you're processing from direct contact with the fuel, but it's in direct contact with combustion gases. So we talked about a blast furnace. The carbon is mixed in with the ore, so it's in direct contact with the material you're processing. And these reverberatory furnaces, the material that you're processing is only in contact with the combustion gases. So molten aluminum is very reactive. So here's an example, aluminum liquid plus SiO2 forming Al2O3 plus Si. And this would be liquid Si, the metallic form. So the free energy change for these reactions, the aluminum
request for the expo.
Okay.
the aluminum metal has a very low free energy of formation, especially compared to SiO2. So it wants to strip the oxygen off of the SiO2 and form Al2O3. Molten aluminum wets and penetrates most refractories. So it's very reactive. It corrodes the refractories. So you have to add an anti-wetting agent, and that's usually 1 or 2% calcium fluoride or barium sulfate. So the calcium or the barium react and form different alumina spinels. That blocks the pores because there's a volume increase in that reaction. So there's another reverberatory furnace. The metal reaction and penetration is the primary issue, especially this type of reaction here. So when you see this reaction, you really can't have silica in the lining of this furnace because the aluminum metal will reduce it. So the roof here, the upper walls above the metal, so they're non-metal contact, can be a brick or castable of the 50–70% alumina type. So they're alumina silica materials, but below the metal line, the floor, the lower sidewalls, where there's metal contact, it's usually a brick and it's a phosphate bonded high alumina. So you're eliminating the silica to prevent that reaction that I just mentioned. And there's a backup lining, can be a brick or castable, and it's usually a lower alumina, like a 50% alumina, can be an insulating fire brick. It could be an insulating castable. The copper smelting furnace, the charge is a copper ore concentrate, and you end up with what's called a copper matte. So the copper ore that's concentrated usually has a copper content in this range, 18 to 30%. And then these are all the components that are in the charge, the copper ore, Cu2S, CuS, FeS, FeS2, and Ag2S. Could be some other oxides and sulfides present also. So you add a slag former to this mix, limestone, calcium carbonate, and silica. So those two form the slag. Again, it's a horizontal reverberatory furnace. So the mixture of metal oxides and these stable oxides, they melt together in this liquid slag, and that takes place at maybe 14 to 1500 degrees C. And then when you cool that, you end up with this copper matte, which is basically Cu2, so a copper sulfate, FeS, an iron sulfate, and Ag2S, a silver sulfate. The silver is a very small component, and you still might have some oxides and other stable sulfides present. So this copper matte goes from 18 to 30% copper to maybe 50 to 60% copper. Fe is about 15%, and then your sulfur is maybe 20 to 25%. So one of the reactions taking place is the copper oxide plus the iron sulfide forming a copper sulfide, copper sulfide, and then the iron oxide. So you're forming these stable copper sulfides in this copper matte. This is a cross section of the furnace. So the main issues here are slag attack, and then reactions with these gases that contain sulfur. So the roof of the furnace, the sidewalls, and the inner working lining for the floor are all direct bonded chrome magnesite brick, high in chrome content. We talked about direct bonded and refractories where the crystals are in direct contact. So this is a high chrome, higher purity chrome magnesite brick. And then it has two backup linings. The first backup lining is a high MgO chrome type brick. And then the second backup lining can be an alumina silica material. So these linings are high in chrome. They're not that corrosive to the copper matte. So you take the copper matte, you put it in a copper converter, and that makes a product called blister copper. So the charge is the copper matte from the smelting furnace. And again, it's a mixture of copper, iron, and silver sulfides. Perhaps other sulfides and oxides are also present. This is a cylindrical furnace. And in the first step, you're oxidizing the iron with blowing air. So the iron enters the slag as an oxide, and you produce a gas, SO2. And that takes place around 14 to 1600 C. And the second step, you add carbon. The carbon reduces the copper to liquid metal, liquid copper, and that takes place at 13 to 1500 degrees C. So you're going to end up with a copper metal, and silver may be an impurity at that point. You may have other impurities present also. So now the copper content in this copper blister is up to 98 to 99%. And in step one, I just mentioned, you're removing the sulfur as SO2. So CuS plus O2 forms CuO, and SO2, or CuS plus O2 forms Cu plus SO2. So step one, you're forming the SO2 gas, and you're also oxidizing the iron. So FeS plus O2 forms FeO and SO2. FeO is collected in the slag. FeO plus SiO2 from the slag also forms this compound, Fe2SiO4, which ends up in the slag. And then eventually step two would be to add the carbon to reduce the copper oxide to metallic form. So this is a cylindrical furnace. You have a slag corrosion and then reaction with gases containing the sulfur. So the hood here is usually a plastic refractory, a chrome alumina plastic. And then basically the working lining is a high MgO chrome refractory brick. So a magnesite chrome brick. And then the tweers where you blow in the oxygen are a direct bonded high chrome magnesite brick again. So I have one failure analysis from a chrome magnesite brick from a copper smelter. This is what the cold face looks like at 20x, and then I did the chemistry here. So it's about a 62% MgO material, about 21% Cr2O3. And then in all of these chrome magnesite bricks, you're going to have some Fe2O3. It's about 10% here, some alumina, about 4%, and some silica, almost 2%. So these are pretty complex microstructures. This is an aggregate. It's the chrome aggregate. So this is about 55% Cr2O3. And then you have your MgO, your alumina, and your iron oxides. This aggregate is a magnesia aggregate. It's about an 85% MgO material. And then it also has some Fe2O3, some silicon, some lime, and some alumina. So you have chrome aggregates, magnesia aggregates, and then the fines in the matrix are about 52% MgO and 26% Cr2O3, plus you have alumina, lime, and silica. These bright grains are also chrome grains. So if you go to 250x, and I think this is right in this location right here, going to higher magnification. You can see your magnesia aggregate, and then the precipitates, these lighter precipitates, are your magnesio-wustite precipitates. So your MgO, Fe2O, MgO, FeO precipitates in MgO. So this particular grade is about 67% MgO and 12% Fe2O3. It has some chrome in it, about 17%, and also some alumina. This is the chrome aggregate. It's about 55% Cr2O3, 19% MgO, some alumina, and some iron oxides. This is another magnesia aggregate, but it has quite a bit of chrome in it. So you can see the dark gray is the magnesia with the magnesio-wustite precipitates, and then you have some chrome in that one. So if you map it, the blue here is the Mg. So you can see the location of the MgO. So there's an aggregate here, here, and this one. The black areas are where the chrome was. So Cr is in green. So here's a chrome aggregate, and then you can see there's a chrome in this grain. There's also some chrome diffused into the MgO. And iron in green here, Fe, is basically uniformly distributed in the chrome aggregates and the alumina, I mean the MgO aggregates. So it's pretty uniform distribution of Fe. And then the blue is the aluminum, and it's concentrated where the chrome is. So that's the coal face. It's a pretty typical chrome magnesite type refractory. And then this is the reaction taking place at the hot face. This is right at the hot face here. So this is basically metallic copper, this spherical particle. It's about 90% copper. It's surrounded by oxidized copper. So CuO is about 70%, plus it contains sulfur, probably copper sulfate. And then this is what's left of the refractory. It's reacted with the slag. So you can see it's low in MgO, low in chrome, but it's primarily the slag, which is rich in silica, the iron oxides, and the copper oxide. And then this is more into the hot phase. This is where the slag layer stops, and this is the original refractory. So this is the slag refractory interface right here. So the slag, right opposite the refractory, has a little bit more MgO in it, but it's, again, silica, the iron oxides, and copper oxide. And then the refractory composition, you can see there's quite a bit of MgO here, but it's also contains silica, the iron oxides, and the copper oxide. So they're diffusing into the refractory at this interface. You can see an MgO grain here and some other chrome grains. So right at this interface, this is a residual chrome aggregate that has floated out into the slag layer. It's still intact, but it's slowly dissolving. So it's about 55% Cr2O3, 20% MgO. There's alumina and the iron oxides. So this chemistry is still intact, but this aggregate is moving outward, intact and slowly dissolving in the slag. This is a chrome aggregate. It's intact. It's about 71% Cr2O3, and there's MgO, alumina, and Fe2O3 present also. And then this is an MgO grain. But you can see this MgO grain contains quite a bit of copper oxide. So the copper that's diffusing in through the matrix is attacking the matrix and the MgO grains. The chrome aggregate is pretty resistant to the slag attack. And then going up into higher magnification, right at this interface here, it looks like this. The dark gray area here is rich in silica, MgO, and then the iron oxide. So this would have been an original MgO aggregate, but it's now been infiltrated substantially with silica and Fe2O3 or FeO. The interface is high in MgO and the iron oxides. And then the slag is high in the two forms of Fe, and there's some magnesium dissolved in it. So that's what's happening at the interface, if you try to place this on a phase diagram of MgO, SiO2, and FeO. We looked at this diagram before when we talked about materials like olivine. 2-MgO SiO2 is phosphorite, and 2-FeO SiO2 is phthalate. So phthalite's the low temperature form, phosphorite's the high temperature form. So you're starting out with a slag interface area with this type of composition. So you have MgO and SiO2. That looks pretty much like the phosphorite. And then as iron is added to that, you're moving in the direction of the arrow. So the slag is dissolving the MgO before it attacks the chrome. And now you're rich in silica, iron oxide, and copper oxide. So iron oxide and silica is over here on this side of the phase diagram. So as you move from phosphorite to phthalate, you can look at the temperature profiles. This is 1800, 17, 15, 16, 15, 14, 13, and 1200. So you're going down in temperature as you react with the phosphorite to convert it to phthalate. So that's pretty much what's happening in this material. The chrome magnesite is by itself is a pretty complex microstructure, and it gets even more complex when you react it with the slag. So this just summarizes what I said. As corrosion takes place, you're moving across this phase diagram. So as the FeO content increases, the melting points are going to decrease. I thought I'd get started on a glass tanks today. And a glass tank simply produces glass from all these different minerals. So silica, soda ash for the sodium source, limestone for the calcium source, potash for the potassium source, a magnesium carbonate for the Mg source, and then borax for sodium and boron. So these are typical components that you would use to form a glass. So this is a reverberatory furnace again. Raw materials are injected in one end of the furnace. The raw materials spread over the molten glass, eventually melt and homogenize. And these are usually run about 1500 degrees C. And then the molten glass passes under a submerged throat that helps separate the unmelted batch from the rest of the material. And then it's drawn off at the exit end, and it goes to some kind of forming operation. So these glass tanks last a long time, maybe 5 to 10 years. So what happens in the glass tank? The reactions, you're decomposing any of the carbonates. The magnesium carbonate would form MgO plus CO2 gas. The sodium carbonate would form Na2O plus CO2. So you're decomposing any of the carbonates to the oxides. And then all these oxides dissolve in each other to form a viscous liquid. And it's primarily a silicate-based glass. So looking at the side here, here's your melting part. This is your glass tank. On each side of the glass tank are the regenerators. So here's your glass at the bottom of the tank. There's a burner over here. There's burners on both sides. So the flame goes over the melt. Here's your roof. So there's a radiation effect here that melts the glass. So when one set of burners is running right on this side, the exhaust gases go over here and through this regenerator. And there's refractory brick in here that heat up. So the hot gases go through the regenerator, heat up these refractory bricks. And this alternates. So the burners are running here, the hot gases go out here and heat this up. And it's drawing preheated air from this regenerator. So the air goes through here, heats up from this hot regenerator, the fuel is burned, and it exits this way. And then when this is cool, it switches. This should now be hot. This regenerator should be hot. So the air comes in here, it's preheated for these burners, and these burners are turned off. And then the hot gas goes through the regenerator again. So that's how a glass tank is operating. This is a simpler version. So looking down at the top, here's your melting area. Here's your refining area. Here's that throat I talked about that separates the batch that's floating on top of the melter from the refiner area. And then these are various refractories line troughs where the glass is carried to different forming operations. So here's one regenerator. There'll be another one on this side. The feed comes in right here at the end of the furnace. That's called the doghouse. These are the burner ports looking at the side now. Here's the throat. And then this is the view we just looked at. The glass tank is right here and the two regenerators. So this is how it's zoned. So this is the glass tank. You have alkali corrosion in the top. So you have alkali vapors that evaporate. They volatilize and attack the crown and upper sidewalls. And in the bottom, you have glass corrosion. So the roof is a brick. It's usually a silica brick. It can also be a mullite or a high alumina brick. The bottom is a fused cast AZS. It could also be a cindered AZS or perhaps even zircon. And then the upper sidewall is fused cast AZS, or it could also be sintered alumina or zircon. And the lower side walls are pretty much all fused cast AZS. So the fused cast material is in the bottom, and the lower side walls that are in contact with the glass, it's the best refractory to use in contact with the glass. And then the regenerators, because you're running hot gas through these or cool air, they're going to have a thermal shock issue. And the alkali that vaporize in the furnace are also going to be carried over into the regenerator. So you have thermal shock issues and you have alkali corrosion issues. So the checker brick have high heat capacity that heat up. The top checker bricks are usually MgO or MgO chrome. That's more resistant to the alkali carryover. In the middle of the checker system, you might have an MgO brick, and in the bottom, where it's cooler, might be MgO or high alumina. And then the crown here and on the top and the bottom and the sidewalls are usually an MgO chrome brick or high aluminum brick. So that's what the refractories look like in a glass tank. I have an example of a silica brick that was taken from a glass tank crown. And next time we'll look at, we'll go through this today, and next time we'll look at the postmortems of some AZS bricks in the bottom of a glass tank. But right now, this is a silica brick from the roof. This is the actual hot face, and then this is the entire piece that was left. So it's a low magnification. This is where the top of the roof is, the cold face. This is the hot face. And then you can't really see it here, but there's a transition region. It'll show up when I do the higher magnification. SEM photographs. This is just a photograph with the camera. So in the hot phase to the transition region, you have glass penetration, and then from the transition region to the cold phase, it's still intact silica refractory. So the roof is subjected to sodium vapor corrosion. So you have Na2O in the glass melt. The combustion gas has H2O. So that forms a gas NaOH. And then that gas NaOH uh, uh, deposits on the refractory surface in the roof, and then it dissolves in the liquid silica. So now you have Na2O dissolved in the silica refractory, and you have your H2O gas coming off. So a diagram of what exactly is happening. Here's your glass melt. It contains primarily SiO2, and then the modifiers in the glass, Na2O and K2O. So Na2O is very volatile. It reacts with the H2O and the combustion gas, and NaOH gas comes off, deposits on the silica refractory roof, and NaOH plus SiO2 forms Na2O. So the Na2O is now dissolving into the SiO2 refractory, and water is a byproduct. So this is a cold phase of a silica refractory. The black is the porosity. So the 20x magnification here, the chemistry in this field of view is about 96% SiO2, and then there's 3% CaO. That's the mineralizer that's added to convert the quartz to tritamite and cristobalite. So we've looked at this structure. The blue is Si, the black is primarily the porosity. And then between the silica crystals, Ca is red, so it's in the grain boundary areas. That's the mineralizer. And then if we go to a higher magnification, uh, these gray areas are the silica, basically 100% SiO2. And then the brighter phase, almost white, is where your lime is. So about 47% CaO and 53% SiO2. And that crystallizes to the wollastonite. So this is a typical silica refractory. It's at the cold phase, still intact. And then this is what the hot phase looks like. This is 20x. The black spots are the pores. So now the silica content is reduced because it's been infiltrated with Na2O. So it's about 93% SiO2, almost 4% Na2O, plus your mineralizer that was present, about 2.5%. So the blue is Si. It's pretty uniform. The red is the Ca. Calcium is the mineralizer. You can see it also in the slag layer that's at the top here. There's a thin slag layer on this refractory. And then the green is the Na. So you can see clearly the green slag layer where the sodium is concentrated. And you can see how far the Na has diffused into the grain boundary areas. It's between all the silica crystals. So Na is diffusing into the hot phase here. And at a higher magnification, this is right at the hot phase. This is the slag layer, or the glass layer, actually. You can see it's rich in Na2O. It's about 16% right here. The balance is silica and your lime is the mineralizer. And then intact below this glass layer is your silica crystals. So this comes out to about 100% SiO2. So you can see it attacking in what used to be the grain boundary areas between the silica crystals. And then the transition zone, and we go all the way back. It's right here. That's where the sodium penetration stops. So again, the black is porosity. This is 20x. And so the chemistry in this field of view, about 94% silica, 4% lime. And then now you have a small amount of Na2O, about 1%. It's these bright areas here at the grain boundaries between the silica crystals. So if you map the elements, here's silicon, it's in blue, it's pretty uniform. You can see the lime, the mineralizer at the grain boundaries between the silica crystals. And then right at this transition zone, you can see the Na penetration in green here, going through the grain boundaries. It's the same areas where the lime is located. If you go to higher magnification at this transition zone, you can see a silica aggregate here and the individual silica crystals. This bright phase here is the wollastonite. And then this phase here in a little bit lighter gray than the silica is the glass phase. So it's about 73% silica, 13% lime, and 10% Na2O. So this is where the Na2O is penetrating. You can see these crystals are only partially intact. They've been dissolved into this glass. So the sodium is penetrating through the grain boundary phases and forming this lower melting material. It's a soda, basically a soda lime silica glass at this point. So if you put this on a phase diagram, here's SiO2, here's cristobalite, here's trinamite, the primary phase fields. This is pointing in the direction of CaO, and this is pointing in the direction of Na2O. So it's not the complete phase diagram. It basically stops at CaSiO2 and Na2SiO2. But we're only interested in this corner where it's silica rich. And if we blow up that corner, this is the composition of the cold phase. It's almost all silica, and this is the direction of CaO. So it's a small amount of lime. So this is the intact silica refractory at the cold phase. This temperature profile is about 1700 degrees C. And then the glass in the transition zone, its composition is right here. And then the glass at the hot phase, its composition is right here. So it's increasing soda and lime contents in both of these. So the refractory is transitioning from this cold phase composition to this composition at the transition zone and to this composition at the hot phase. If you look at the temperature profiles, this one's 1700, 1600, 1500, 1400, 1300, and 1200. So these compositions are going to be molten at 1200 degrees C. And that's how the corrosion is taking place. The sodium infiltrates the grain boundaries, forms these lower melting materials, and eventually dissolves the silica. So that's what I have right now. We'll continue with a postmortem study on some other silica not silica refractories, but other refractories in the glass tank, especially the AZS next time. So I will see you again on Wednesday. Have a good rest of your day, and we'll finish up glass tanks on Wednesday. Again, thanks for listening.